Hello, I hope you guys can hear me. I'm going to be studying differential equations again. Um, I'm just gonna start studying from where I last left off. Okay, let me change to full screen. So last time I did directional fields and numerical methods. I remember directional fields. I don't remember what do they mean by numerical methods. This is taking time to load. Okay, so I remember all of this about the equilibrium solution and Euler's method. Actually, uh, let's do one question about Euler's method. Hmm. Estimate the following solutions using Euler's method with n is equal to 5 steps over the interval t 0 to 1. Hold on. Um, if you're able to solve the initial value problem exactly, compare your solution with the exact solution. If you're unable to solve the initial value problem, the exact solution will be provided to you to compare with Euler's method. Okay, let's try a hmm, okay, let's try 97, I guess. Question 97. Derivative of y is equal to y plus sorry, y plus t square. Okay, and y0 is 1. Sorry, y0 is 3. The exact solution is y is equal to 5 e to the power of t minus 2 minus t square minus 2t. Okay, hold on. Let me think about this. Hmm. I don't need this. Just need these two. So I'll do this. D 0, then y is 3. The derivative of y 3 plus 0, so 3, right? And then the next step would be with n is equal to 5 steps. The next step would be 1 over 5. To 0 0.2. 0 0.2, 0 0.4, 6, 0 0.8, 1, 2, 3, 4, 5. Is this right? Okay, now we do so y 0 0.2 is equal to the initial y plus the derivative at y 0 0.2, I guess. This is correct. So then this is y0 is 3 plus it with 3 times 0.2, 0.6, which gives 3.6. Okay. The derivative will always remain 3, right? I mean, this derivative isn't going to change. So 3.6, and then y is 0.4 is equal to y 0.2. We are going 0.2 steps ahead. And then this at 0.2, and then 0.2 steps. Let me just take all this, put it here. Do we find the derivative at 0.2 or at 0.4? No, it's the previous one. Okay, I think that makes sense. Because like, here is the graph. Taking this derivative, this is the new point. And then taking the difference in x, multiplying it with the derivative at this point, and then getting the approximate value here. Then this is 3.6 plus 3.6 times it by 0.2. $4.32. Now let's try wait, why is this 0. No, wait. I think this is wrong. No, this is wrong. Hold on, all of this is wrong. So y 0.2 is equal to y0, the derivative at 0.2, no, the derivative at y0, derivative at 0, Oops, I don't know why I keep doing this. And then 0.2. So what we are doing is we're taking the previous value of y and then adding the jump. So 0.2 times the gradient plus the previous y value, that will give the new y value. So that is y0 is 3, and then derivative at 0 is 3 plus, so it's 3 times 0.2. Three plus 3.0.2. Just write it here. This is 3. The first one was correct. Zero 0.6. Then the next derivative at 0.2. So 3.6 plus 0.2 square. I get 3.64. I hope I'm correct. And then y 0.4 is equal to the previous one plus the jump. And then the step size is 0.2. This is equal to 3.6, 3.64, 0.2. 4.328. The derivative is the y value at 0.4 plus it with 0.4 squared. 4.328 plus it with 0.16. And if you plus that with 4 point, plus that with 4.328, 4.488. I'll just do one more and then um actually no, I'll just end it here. So 97 question 97. Y is equal to 3. Let's plot this. Y is equal to 3x. Oops. Y is equal to 3x. Now y is equal to 5. 5 e to the power of x minus 2 minus x squared minus 2x. So let's do this. F of x. F of 0 is 3. 3.667 and then 0 0.4, 4.499. What is this exactly? On the right path. Question 97, 4.2. Section 4.2 exercises. I think they want us to find the estimated solution at um at 1. What's the value of 5e? 5e minus 1. It's very far off. I guess this is correct. Well, I hope I'm right. Okay, anyways, next question. Separable equations. A separable differential equation is any equation that can be written in the form derivative of y is f of x times g of y. The term separable refers to the fact that the right hand side of the equation can be separated into a function of x times a function of y. Examples of separable differential equations include x squared minus 4 times 3y plus 2, only x over here, only y over here, and then this one. The second equation is separable with f of x is equal to 6x squared plus 4x and g of y is 1. The third equation is also called an autonomous differential equation because the right hand side of the equation is a function of y alone. If the differential equation is separable, then it is possible to solve the equation using the method of separation of variables. Check for any value of y that makes gy is equal to 0. These correspond to constant solutions. Rewrite the differential equation in the form dy over gy is equal to f of x times d of x. Integrate both sides of the equation. Solve the resulting equation for y if possible. If the initial condition exists, substitute the appropriate values for y and x for x and y into the equation and solve for the constant. It is not always possible to obtain y as an explicit function of x. Find a general solution of the differential equation. Derivative of y is x squared minus 4, 3y plus 2 using the method of separation of variables. Okay, let me try. Derivative of y x squared minus 4, 3y plus 2. So f of x is equal to x squared minus 4. Then g of y is 3y plus 2. And then we are supposed to write it. So this over here is dy divided by plus 2 is equal to square minus 4 d of x. Then I'm supposed to do this. This will give a if I do a derivative of ln 3y plus 2, I get this, right? So derivative of the inside is 1 over 3y plus 2. Derivative of the outside is 1 over 3y plus 2. Then derivative of the inside is just 3. Then this becomes then integrating this over 3 minus 4x plus c. And then I can do this. Four times 3 is 12 plus c, and then 3y plus 2 is e to the power of minus 12x. I can separate out this plus c separately, so I can do a constant called capital D, right? And then y is equal to minus 12x d minus 2 over 3. Yes. Solving an initial value problem. Use the method of separation of variables. Solve the initial value problem. Wait, how did we solve it before then? Oh, there was no y inside the thing. There was no y value, that's why. So y0 is 5. Mhm. We can just simply integrate it, right? Yeah, that's why I was able to solve it. Okay, let's do the other question. Derivative of y is equal to 2x plus 3 y squared minus 4. 2x plus 3. Okay, let's do this then. Y squared minus 4. If we integrate both sides, this is x squared plus 3x plus c. The problem is this. Hold on. Um, Derivative of arc sine is, nope. Derivative of arc sine h, was it tan h? Is minus 4. Trying to remember how to integrate this. Method of partial fraction decomposition. Okay. Um, yeah, actually. And then 1 is equal to, and then what? Oh yeah, if y is equal to 2, this leads to 1 is equal to 4b. If y is minus 2, this equals to is equal to minus 4a. One over 4. Can extract this out, but the b comes first. Minus y plus 2. Yeah. Then going back to our integration, x squared plus 3x plus c. Ln of y minus 2 minus it with ln of y plus 2. Then ln of 4 times 3 is 12. And multiplied by d. Wait, for the previous one, Yeah, I forgot to, because I did this directly without considering the modulus. Oh, because if I'm writing plus minus, the constant can have either sign. Wait. Yeah, I guess that makes sense. The constant is going to be plus minus. But then where would I go from there? Y plus 12. Can't we extract 4 as well? Then e to the power of 4. Never mind. Plus 2. Same thing. Okay, I was talking about this x square plus 3x to the power of 4 minus it with y x square. I bring to this 2 over here. Instead of writing minus 2, I can write minus 1. I can extract y from here also. 1 minus, and then this becomes. So let me see this again. 2 times x square plus 3x uh, 4d minus 1. Is that correct? extract 2 out. Uh, Hold on, why is that plus? Yeah, this is plus. And then y0 is equal to 1. 1 is equal to 2 times 1 plus 0, 1 plus t, and then 1 minus t. Is this correct? Let me see. Um, Minus t is equal to 2 plus t, 2 plus 2d. Two minus 1, which is 1. D is equal to 1 over 3, which is not correct. Why am I getting this? Two plus two. Okay, I need to understand why I'm getting this. So 1 is equal to 2 plus 2c2, e to the power of 0 is 1. Oh, it's negative 1. This is negative 1. If I put this here, I get minus 1 plus d. So I get 3d. No, I get a single d. So d, and then, yeah, this makes sense. Applications of separation of variables. Solution concentrations. Consider a tank being filled with a salt solution. We would like to determine the amount of salt present in the tank as a function of time. We can apply a process of separation of variables to solve this problem and similar problems involving solution concentration. Uh, a tank containing 100 liters of brine solution initially has 4 kg of salt dissolved in the solution. At time t is equal to 0, another brine solution flows into the tank at the rate 2 liters per minute. This brine solution contains a concentration of 0.5 kg per liter of salt. At the same time, a stopcock is open at the bottom of the tank. What's a stopcock? Allowing the combined solution to flow out at the rate of 2 liters per minute, so that the level of liquid in the tank remains constant. Find the amount of salt in the tank as a function of time measured in minutes. And find the limiting amount of salt in the tank, assuming that the solution in the tank is well mixed at all times. So 100 liters of brine initially has 4 kg of salt dissolved in the solution. t is equal to 0, another prime. This is 2 liters per minute, 0.5 kg of salt. Find the amount of salt it takes in the tank. It's a function of time. Find the limiting amount of salt in the tank. So salt, the amount of salt at t is equal to 0 is 4 kg. S T, I will write text. S T is the salt in kgs, amount of salt in kg at time t. In minutes. It's 0 right now. Tank containing 100 liters of brine solution initially has find the limiting amount of salt. Okay, this brine solution contains a concentration of 0.5 kg per liter of salt. Um, the derivative, like how much salt is being added, 0.5 kg per liter. Kg per liter times it by 2 liter per minute, which is 1 liter per minute. Sorry, 1 kg per minute. And this is constant. But at the bottom of the tank, allowing the combined solution to flow out at the rate of 2 liters per minute. So the level of liquid in the tank remains constant. So how much is flowing out? I think I should do like this. So 1 is adding per minute, 1 kg per minute, and how much is flowing out per minute? Flowing at the rate of 2 liters per minute. I think it's this. 1 kg per minute pouring in, minus it with amount of salt, the currently remaining amount of salt, and divide it by I have no clue. Yeah, inflow rate minus outflow rate, which is what I was doing. Inflow rate is 1 kg per minute, and then outflow rate is unknown, 2 liters per minute. Outflow rate, inflow rate represents the which the salt enters the tanks. Therefore, inflow rate is equal to 1. But how do we calculate the outflow rate? The number of kilograms of salt in the tank at time t is equal to ut. Thus, the concentration of salt is ut per 100 kg liter. Oh, I see. Uh, 100 liters. This is the amount of salt. So it salt in solution is equal to the amount of salt in kgs inside the solution divided by 100, because the divided by 100 liters, kg per liter. The outflow rate is 2 liters per minute. The solution leaves the tank at the rate of 2 liters per minute. Okay, so um, in out is equal to 100 times it by 2. liters per minute. Is this correct? 1 minus s of t. S of 0 is 4. So what are we trying to find? Find the amount of salt in the tank as a function of time measured in minutes. Hold on. D D D D is equal to 50 minus then, and then I get ln. But I can do it like this. I can take like minus out. Can put this minus over here. Because if I bring minus 1 here, then it's minus and plus. D plus C. C minus C. It's e to the power. Now since we don't know C is plus or minus, we can remove the modulus. And then we can separate e to the power of C. Since s0 is equal to 4, 0, 1, t plus 50 is equal to 4, ds. Why is it minus? Hold on. 50 minus u minus 50 plus u. I don't understand. Hold on, what's going on here? I think they made a mistake, maybe. Maybe I did. Minus 50 plus. D is equal to minus 46. So I got the equation. And the next one they're asking, find the limiting amount of salt in the tank, assuming that the solution in the tank is well mixed at all times. This is when t is infinity, and then it will be equal to 50. Note that this was a constant solution to the differential equation. If the initial amount of salt in the tank is 50 kg, then it remains constant. If it starts at less than 50 kilograms, then it approaches 50 kilograms over time. What if it was more than 50? Okay, let's do the next one. The logistics equation. I think I will do 4.5 as well. To model population growth using a differential equation, we first need to introduce some variables and relevant term. The variable t will represent time. The units of time can be hours, days, weeks, months, or even years. Any given problem must specify the units used in that particular problem. The variable p will represent population. Since the population varies over time, it is understood to be a function of time. Therefore, we use the notation Pt for the population as a function of time. If Pt is a differential function, then the first derivative dp over dt represents the instantaneous rate of change of the population as a function of time. In exponential growth and decay, we studied the exponential growth and decay of population and radioactive substances. An example of an exponential growth function is p of t is equal to p0 e to the power of rt. In this function, pt represents the population at time t. p0 represents the initial population. Population at time t is equal to 0, and the constant r, which is more than 0, is called the growth rate. Figure 4.18 shows a graph of Pt is equal to 100 e to the power of 0.03 t. P0 is 100, r is 0.03. We can verify that the function Pt is equal to P0 e to the power of rt satisfies the initial value problem. This differential equation has an interesting interpretation. The left-hand sides represent the rate at which the population increases or decreases. The right-hand side is equal to a positive constant multiplied by the current population. Wait, if we integrate this, would it be p0 e to the power of rt plus c? Okay, anyways. One problem with this function is its prediction that as time goes on, the population grows without bound. This is unrealistic in a real world setting. Various factors limit the rate of growth of a particular population. The growth constant R is the growth constant R usually takes into consideration the birth and death rates, but none of the other factors. And it can be interpreted as a net percentage growth rate at per unit time. A natural question to ask is whether the population growth rate stays constant or whether it changes over time. Biologists have found that in many biological systems the population grows until a steady state population is reached. This possibility is not taken into account with exponential growth. However, the concept of carrying capacity, allowing for the possibility that in a given area only a certain number of given organism or animal can thrive without running into resource issues. The carrying capacity of an organism in a given environment is defined to be to be the maximum population of that organism that the environment can sustain indefinitely. Hold on. We use the variable k to denote the carrying capacity. The growth rate is represented by the variable r. Using these variables, we can define the logistic differential equation. Let k represent the carrying capacity for a particular organism in a given environment, and let r be the real number that represents the growth rate. The function pt represents the population of this organism as a function of time. The constant p0 represents the initial population of the organism at time t is equal to 0. Then the logistic differential equation is dp over dt is equal to rp 1 minus p over k. K is the carrying capacity. K is the maximum population. So it's like RP, but the derivative will get closer and closer to 0, right? This logistic equation was first published by Pierre Wurzel in 1845. This equation can be coupled with the initial condition P0 is equal to P0 to form the initial value problem for PT. And there's a lot of reading here. Suppose that the initial population is small relative to the carrying capacity, then P over K is small, possibly close to 0, thus the quantity in parentheses on the right hand side is close to 1. Okay, now suppose that the population starts at a value higher than the carrying capacity, then P over K is more than 0. Then the right hand side is negative and the population decreases. As long as P is more than K, the population decreases. It never actually reaches K because dP over dt will get smaller and smaller, but the population approaches the carrying capacity as T approaches infinity. This analysis can be represented visually by way of a phase line. A phase line describes the general behavior of a solution to an autonomous differential equation depending on the initial condition. For the case of the carrying capacity in a logistic equation, the phase line is shown as this. Now in differential equation, I'm going to get closer and closer to k and further away from 0. We don't really care about the negative, right? I mean the ones below 0. This phase line shows that when p is less than 0 or greater than k, the population decreases over time. What do they mean by p less than 0? When p is between 0 and k, the population increases over time. Okay, this is getting more complicated than I thought. Okay, let's see. Let's consider the population of white-tailed deer in the state of Kentucky. The Kentucky Department of Fish and Wildlife Resources sets guidelines for hunting and fishing in the state. Before the hunting season of 2004, it estimated a population of 900,000 deer. Shouldn't it be plural? Johnson noted a deer population that has plenty to eat and is not hunted by humans or other predators will double every 3 years. This observation corresponds to a rate of increase R, which is equal to ln of 2 over 3. So the approximate growth rate is 23.11% per year. The KDFWR also reports deer population densities for 32 counties in Kentucky, the average of which is approximately 27 deer per square mile. Suppose this is the deer density for the whole state. The carrying capacity K is 39,732 square miles times 27 deer per square mile, or 1,072,764 deer. For this application, we have initial population 900,000, K is 1,072,764, and R is 0.2311. Substitute these values into equation 4.1 and form the initial value problem. So let's see. So normally, like for exponential growth, we don't add plus C, right? So for example, P0 e to the power of this is how they wrote it. This is how the simple one is. R is the growth rate. Let's do T instead. Right. So this is the initial population, and then our growth rate is K. This is a negative. Now I was thinking of something. So if we do plus 5, we don't add a plus C, right? Because we assume that it's the bottom line is 0, the limiting. You go infinitely back, we reach 0. One minus P over K. Is it 6? 6 is a million, right? It's 5. Then K is, and then R is ln of 2 over 3. Would the half-life still be the same if the equation is different? Ln of 2 over 3. Uh, Constant P0 represents the initial population. I think this is supposed to be P0. They made a mistake here. Anyways, ln of. Would the half-life be the same if the equation is different? Seven two seven six four. Solve the initial value problem from part A. Hmm. And let me find an approximate value for this. 1, 2, 3. 72764 times it by ln of 2 over 3. 0.938 1938. 0.1938p. No, I don't think I'm supposed to do this. This is... I'm supposed to simplify the above. Or, wait, hold on. No, I made a mistake. This is like this. And then 0.231. Um, 2.154. P square. This is going to be difficult. Do I need partial fractions for this? A partial fraction is when you're using constants, right? What's 3 times 72764? 3218. 3218292. 3218292. DP. Or wait, maybe ln of 2/3 can stay here. And then I can write like this. Mm. I'll just write K instead. K, P, nope. K minus P. Multiplying above and bottom by K. And then this is B, P. P is equal to 0. Is equal to P is equal to 0. A is equal to 1 over K. Then if P is minus K, sorry, if P is K, then B is 1 minus. Let me think about this. P is 0. Okay, if P is positive K. No, B is also like this. If P is 0, then 1 is equal to AK. If P is positive K, then 1 is equal to B. Okay, this makes sense. Then if I separate it into partial fractions, both of them will be 1 over K, and then it will cancel out with this K. Plus it with C. Then I get ln of P. Pk minus P square. Is this correct so far? Okay, they did use partial fraction, but why is there 1 over k out here? If k and k cancels out, there's I don't know 2 over 3. I guess that makes sense. Why is this minus? Kp k minus p plus. Oh yeah, that makes sense. So then we are left with I'm assuming p would never be greater than k, so this will always be positive. Then you're left with p is equal to bringing k minus p to this side. And then I can bring this over here. E ln of 2 over 3 d and then 1 plus e. Is this right? So k d. Yes, that is correct. Now next what? Solve the initial value problem. Oh, we have to determine. So p0 is equal to k t over 1 plus t, and p0 is 900,000. Is it? Was it this? T is equal to, I'll just write p0. p0 over k. p0 over k plus it with p0 over k d. Is this right? If I bring 1 over d over here, and then divided by k. T is equal to 1 minus p0 over k. So fraction is equal to p0 divided by k, which is this. And now I have to do f over 1 minus f over 1 minus 5.209. Is this correct? Yes. Therefore, t is equal to around approximate. Now what? According to this model, what will be the population in 3 years? We call that the doubling time predicted by Johnson for deer population was 3 years. With the t, the input, is it in years? Hold on. T is in years, right? So uh, P is 3. K is equal to 72764. And then P0 is equal to 3. One more. And then forget this. No, actually bring it back. And then the constant D is equal to P over K. P0 over K, and then 1 minus P0 over K. And now we do K times it by e to the power of ln 2 1 plus ln 2 d. Okay. So the population this is the population function, right? Pt is equal to t Where is the population? Oh, it's too high. I just divided by a million. Population divided by. Okay, so 900,000, and then in around 2 years, it will be 1,023,639. What's the dividing this number by? I don't understand. The constant is correct. Ln of 2 over 3. Oh, we need it in 3 years. I don't understand why is this the issue. Um, oh, this is why. Or maybe not. 2 or 3. Oh, that makes more sense. So 900, 900,000, 978,817. And what are they asking? Suppose the population managed to reach 1,200,000 years. What does the logistic equation predict will happen to the population scenario? So if it goes to infinity, if t goes to infinity, this would be 1. Why is it none? What number is it reaching? So P T is equal to K R T over 1 plus. I'll divide the upper part by e to the power of RT, also the lower part. So I'm left with this. As t goes to infinity, this part reaches 0, and then this part reaches 0. Yeah, and then d divided by d, and then we reach k. Oh yeah, that makes sense. K is defined like that. I don't know why I was calculating. So this is the upper limit. So it will go, if the population is too high, it will go back to this maximum limit. Okay, so we did all this. The solution is this, right? We will replace k with this. I mean, we will replace t. So pt is equal to k times it with p over k. Mm. Now what? This k and k cancel. So we are left with p0 e to the power of rt 1 minus p0 over k. Then on the bottom, plus p0 over k and then this and this cancel out. So we are left with um, I took B0 over K out. I'm left with this. I guess I can do K over K minus this. And then this K would go over the top, right? Hold on. Whoops, it's 1 plus. Okay, I'll just add plus 1. Yeah, I think this is correct. We state this result as a theorem. But how do we, growth rate isn't a constant, right? I mean, it's a constant, but it doesn't express like uh, how long the it doesn't pause remain, it doesn't represent the exact growth rate. If these two are minus, I think the graph would be reversed. It will be going down. Wait, where was I? Here. A solution to the logistic differential equation is this. Working under the assumption that the population grows according to the logistic differential equation, this graph predicts that approximately 20 years earlier, the growth of the population was very close to the exponential. The net growth rate at that time would have been around 23.1% per year. As time goes on, the two graphs separate. This happens because the population increases and the logistic differential equation states that the growth rate decreases as the population increases. At the time the population was measured, uh, it was close to carrying capacity. The population was starting to level off. The solution to the logistic differential equation has a point of inflection. To find this point, set the second derivative equal to 0. I see. So the point of inflection is when the derivative is positive and then it becomes negative. No, when the change in derivative is positive and then the derivative is slowing down. So that's where the second derivative is 0. Which is minus infinity. This entire quantity will be non-zero as long as p0 is not equal to k. So then we are left with this, which has the possibility of being 0. Notice that if p0 is greater than k, then this quantity is undefined. The graph does not have a point of inflection. In the logistic graph, the point of inflection can be seen as the point where the graph changes from concave up to concave down. This is where leveling off starts to occur, because the net growth becomes slower as the population starts to approach a carrying capacity. Alright, that's good. Wait, I just want to check if my YouTube is still working. And then I guess I'll go to the next chapter. So these questions take so long. But I guess they gave the equation at the end, so we can just substitute in the values. This k and k cancel, so we are left with p0. Okay, let's go to the next chapter. First order linear equations. Earlier, we studied an application of a first order differential equation that involved solving for the velocity of an object. In particular, if a ball is thrown upwards with an initial velocity of v0 feet per second, then an initial value problem that describes the velocity of the ball after t seconds and is given by this. This model assumes that the only force acting on the ball is gravity. Now we add to the problem by allowing for the possibility of air resistance acting on the ball. Air resistance always acts in the direction opposite to motion. Therefore, if an object is rising, air resistance acts in a downward direction. If the object is falling, air resistance acts in an upward direction. There is no exact relationship between the velocity of an object and air resistance acting on it. For very small objects, air resistance is proportional to velocity. That is, the force due to air resistance is numerically equal to some constant k times v. For larger baseball-sized objects, depending on the shape, air resistance can be approximately proportional to the square of the velocity. In fact, air resistance may be proportional to v to the power of 1.5 or v to the power of 0.9 or some other power of v. We will work with linear approximation for air resistance. If we assume k is more than 0, then the expression for the force Fa due to the air resistance is given by Fa is equal to negative kV. Therefore, the sum of the forces acting on the object is equal to the sum of the gravitational force and thus the force due to air resistance. This in turn is equal to the mass of the object multiplied by its acceleration at time t. This gives us the differential equation mdv dt minus kv minus mg. Ball is falling down, right? Why is this minus mj? Why are both of them minus? Shouldn't one of them be positive and one of them negative? The differential equation in this initial value problem is an example of a first order linear differential equation. A first order differential equation is linear if it can be written in the form a one function derivative y plus one function derivative another function y equals c of x, where a, b, and c are arbitrary functions of x. Remember that the unknown function y depends on the variable x, that is, x is the independent variable and y is the dependent variable. Some examples of first order linear differential equations are sin x. Okay. first order non-linear differential equation. Key standard form. Consider the differential equation. Our main goal in this section is to derive a solution method for equations in this form. It is useful to have the coefficient of y, coefficient of derivative of y be equal to 1. To make this happen, we divide both sides by 3x squared minus 4. This is called the standard form of the differential equation. We will use it later when finding the solution to a general first order linear differential equation. Returning to equation 4.14, we can divide both sides the equation by 8ax. This leads to this. Now define p of x and q of x. Okay. Put each of the following first order linear differential equation into standard form. Identifying p of x and q of x. So over here, put 4y to the other side. We get derivative of y plus 4y is equal to 3x. So qx is 3 and px is 4 plus 4. Yeah. Okay. Integrating factors. We now develop a solution technique for any first order linear differential equation. We start with the standard form of a first order linear differential equation. The first term on the left hand side of equation 4.15 is the derivative of the unknown function. The second term is the product of a known function with the unknown function. This is somewhat reminiscent of the product rule from the differentiation rule section. If you multiply equation 4.16 by yet to be determined function ux, then the equation becomes ux is uxb. Yeah. The left hand side can be matched perfectly. Derivative of the first times the second. Derivative of the first times the second. Matching term by term gives y is equal to f of x. G of x is ux, and derivative of g of x is ux px. Taking the derivative of g of x is equal to ux. Setting it equal to the right hand side of leads to this. This is a first order separable differential equation for ux. We know px because it appears in a differential equation we are solving. Separating variables and integrating yields this ln of ux. Here C2 can be an arbitrary constant. This leads to a general method for solving a first order linear differential equation. We multiply both sides of equation 4.16 by the integrating factor ux. This gives this. The left hand side can be written as wait, I don't understand. Derivative of u is ux px, right? So how are you getting this? Oh, yeah, yeah, I see. Oh, now I understand. Ux. You're rewriting this whole section as this, and this remains the same. Now we integrate both sides with respect to x. Okay, dividing both sides by ux gives this y is equal to 1 over ux qx dx plus c. Since ux was previously calculated, we are now finished. An important note about integrating constant c: it may seem that we are inconsistent in the usage of the integrating constant. However, the integral involving p of x is necessary in order to find an integrating factor for equation 4.15. Only one integrating factor is needed in order to solve the equation. Therefore, it is safe to assign a value for c for this integral. We choose c is equal to 0 and calculating integral inside the bracket. Put the solving a first order linear differential equation. Put the equation into standard form and identify p of x and q of x. Calculate the integrating factor u of x. Multiply. Okay, this is complicated. Find the general solution for the differential equation. This assume x is more than 0. This is going to be difficult. X 3y equals 4x squared minus 3x. Then we are left with 3 over xy pq and qx. So px is 3 over x. Then that means, yeah, let's find the integral first. Three ln of x guess e to the power of x cubed, like that. Hold on. Multiply all the sides with x, and then we get this. This is done by solving this. I did not add the constant, did not add the plus c. No, no, no. And then u of x is such a function that derivative of ux is equal to u of x times p of x, and then times y is equal to u of x, u of x. Is this right? Yes, this is right. If we integrate uh, times it by d, times it by d, and then integrate it with 4x minus 3. No, wait. See. The d and uh, d would cancel out. The d which is multiplying here would cancel out with this d. Also, instead of e to the, I guess I can remove this. Assume x is always more than 0. Okay. In the question, it telling us to assume it's more than 0. X cubed, and this is and then is this correct? X to the power of negative 3 for x squared. Okay, let's see. Yeah, that is correct. Is there anything new? Nope. So let's try let's see what this is about. Electrical circuits. Should I pray for it? Air resistance. Okay, let's do this one question, and maybe you'll start reading about electrical circuits. Racquetball is hit straight up with an initial velocity of 2 meters per second. The mass, hold on, is my YouTube still working? Rules section. Okay, anyways, the mass of the racquetball is approximately 0.0427 kg. A resistance acts on the ball with a force numerically equal to 0.5 v, where v represents the velocity of the ball at time t. Find the velocity of the ball as a function of time. So ball is hit straight upwards. Initial velocity of 2 meters per second. The mass of the racquetball is 0.042 kg, 427 kg. Air resistance acts on the ball with a force numerically equal to 0.5 kg. Force of air resistance is equal to, I think capital A is easier to, never mind, 0.5 V. So ball is going upwards. Air resistance is slowing down the ball, right? So it should be minus, and then air resistance, gravity, where V represents time t. How long does it take? Find the velocity of the ball as a function of time. I will call this air resistance R. So velocity is it's disconnecting again. Minus it with 0.419. Now PT is equal to 0.5, QT is equal to and now ut is such a function that the derivative is equal to ut pt. That means ut plus pt. Vt. No, it's UTPT. UT. Now you can rewrite this upper part as UTVT. It's a derivative of the first times the second plus the first times derivative of second. And now integrating both sides. Whoops. Now integral of pt with respect to t is equal to 0.5 plus c, 0.5 t plus c. So ut is equal to e to the power of 0.5 t. I can write t. So then v t is equal to 1 over but I can write d but it will cancel out later. Qt is minus 0.419. I'll write minus here. 0.419 and then the d cancels out. All of this is a no here. Hey, what's the integration of? I think it's this. If I derivate all this, get this constant is separate, e to the power of 0.5. Derivative of this is e to the power of 0.5 times 0.5, right? Okay. And this is equal to this and this multiply. Wait, hold on. Now let's see how correct I was. I made a mistake somewhere. Um, let's see. Derivative is minus this, minus this. Um, the net force, which is mass times acceleration. I see. So I made a mistake. Minus 0.4. Dividing it by 0.0427. So m times mm, instead of 0.5, it's 11.71. 11.71. So I have to remove this. 11.71. 11.71. This is 11.71. So is this correct so far? Uh, I don't get what's happening here. Oh, this part remains 9.81 because the mass is divided. Negative 9.81. QT 9.81 here as well. The negative is here. Nine point eight one divided by 0.8377. 0.83. Let's just do 0.84. So V0 is equal to 2. So then 2 is equal to 0.84 minus C. C is equal to wait, hold on. If this were to be plus C, C would have been 2.84. Hold on a minute. plus 2.84 over e to the power of uh, at x is equal to 0. But how would we know whether the constant is positive or negative? Because I wrote plus c here. Okay, never mind. I'll think about it later. Plus, plus. But the thing I'm confused by is when we integrate this, if I take the minus outside, then integrate, I'm left with minus 1 here, and then this becomes minus c. Shouldn't minus c and plus c both give the same answer? The ball reaches its maximum height when the velocity is equal to 0. The reason is that when the velocity is positive, it is rising, and when it is negative, it's falling. How long does it take to reach its maximum height? So then the derivative is 0. This is 0. And then we just have to find the value of Vt we substitute the equation for Vt over here, set this to 0, and then we just find the value for t. If the ball is hit from an initial height of 1 meter, how long will it reach? How high will it reach? So I guess we take the velocity function, integrate it from time t is equal to 0 to t is equal to integrate it from t is equal to 1 to t is equal to the time it takes to reach maximum height. So t is about 0.104. Yeah, we need to integrate. Let's try integrating this. So integral of what's the formula? 2.84 71t negative from 1 from 1 to from t is equal to 0 to t is equal to 0.104. 11.711. And then whatever the final value is, I have to offset it by 1. So we take this 0.104 minus 0.84, then minus 0.84 again. Minus 0.84, then when this is 0, No, wait, this is wrong. So all this minus it with when it's 0. Oops, it's minus 0.4 t. So 104, and then if this is 0, this will be 1. So then copy all this, copy, paste, and t is equal to 0, so this is gone, and this here will become 1. And then we offset it by 1, so it's 1.083. Yeah. So electrical circuits. Source of electromotive force, battery or generator, produces a flow of current in a closed circuit. And this current produces a voltage drop across each resistor, inductor, and capacitor in the circuit. Kirchhoff's loop rule states that the sum of the voltage drops across resistors, inductors, and capacitors is equal to the total electromotive force in a closed circuit. We have the following three results. The voltage drop across the resistor is given by this, where R is a constant of proportionality called the resistance and I is the current. The voltage drop across an inductor is this, where L is the constant of proportionality called the inductance, and I again denotes the current. Why do they represent voltage with E? The voltage drop across a capacitor is given by this, where C is a constant of proportionality called the capacitance, and Q is the instantaneous change on the capacitor. The relationship between I and Q is I is equal to derivative of Q, the instantaneous charge on a capacitor. We use units of volts to measure voltage, E, amperes, A to measure current I, and coulomb C to measure charge Q, ohms to measure the resistance, henries to measure inductance, and farads to measure capacitance. If there's no capacitor in the circuit, then the equation becomes this. This is the first order differential equation in I. The circuit is referred to as an LR circuit. Now suppose there is no inductor in the circuit, but there is a capacitor and a resistor. Then the equation can be written as, which is a first order linear differential equation. This is referred to as an RC circuit. In either case, we can set up and solve an initial value problem. RC circuit, LR circuit. Is there a CL circuit as well? Okay, I think I will end this stream here. In the next chapter, we will learn sequences and series. Actually, you know what? Let's do this question. E is equal to 50 sine 20 TB. Resistor of 5 ohms. Yeah. I thought that V was a variable. An inductor of 0.5 Henry. If the initial current is 0, find the current at time t, which is more than 0. Yeah, I have this equation. So PT plus PTI plus which is equal to QT, and then multiply it all by U. Yeah, hope I'm doing this right. Is equal to UT QT. Then integrate both sides. Now UT is such an equation that, wait, hold on. Hold on a minute. Okay, so ut is such an equation that derivative of ut is equal to ut times pt. With respect to t is r over lt. Ut is e to the power of this. So then ut times qt one over e to the power of r t over l, and integrate all of this. Hold on, I didn't change to full screen. So anyways, I was doing this. Integration of pt is r over lt, because pt is r over l, and then ut is equal to e to the power of rt over l, and then we continue ut times qt, which is, and then qt is e over l. But e over l is a constant, so um and then, yeah, this is the solution, and then current, if the initial current is 0, so if I is 0, e to the power of l l to the power of r, this becomes 1, e over r becomes 50 psi. Hold on, I did not substitute E. This is all wrong. I need to substitute the values. So R over L, 5 over 0 0.4, 12.5. 0 0.4. 50 sine. 50 times 0 0.4 is 20. But I can just take 20 outside. This looks... I don't even know if this is correct. Oops, it's 50. Where did the 50 go? I mixed up 50 and 20. No, wait. I did not mix it up. It's 20 over here and 20 over here because 50 times 0 0.4 is 20. Why is this 125? E over L. 50 divided by 0. Yeah, it's 125. I made a mistake. But then what's the integration of this? How did they integrate this? Okay, anyways, this is the final answer. Then set I to 0 and we get the C. But I don't understand. How do you integrate? Do you use integration by parts? UDV. Yeah. Yeah, I mean, I already saw the answer, but I'm guessing you use integration by parts. Okay, anyways, I will just end the stream here. And next topic, we will learn about sequences and series. So I want to know how I want to get a reminder on how they got the formula for U. Okay, ln of U plus C. And the sign would depend on the C. But I don't, we don't need C2 since we'll integrate this and there will be plus C over here. Okay, I will end the stream here then. And yes, I'll see you guys next time.